All right, question 17 on the math subject GRE practice test. So I kind of enjoyed solving this problem because it just worked out kind of perfectly and I solved it in like 10 seconds. What happens is I kind of glanced at the instructions and was like, all right, I got this infinite sequence of real numbers. Now I'm trying to figure out what the false statement is. So I look over here and I consider A, really hoping that it's false, right? Because if it's false, then I'm done with the problem. And what A says is that every unbounded sequence is divergent. And unfortunately, that's a true statement, but it's very similar to a false statement. As we'll see when I go through these, the converse of this statement is false. Unbounded implies divergent, but divergent does not imply unbounded. So when I looked at A, I was hoping it said every divergent sequence is unbounded, and I would have been like, awesome, that's false, I'm done. But it doesn't. So at first I was a tiny bit disappointed. But then I came down to B, and I realized what B says is essentially, or equivalent to, that exact statement that I was hoping to see up in part A, that every divergent sequence is unbounded. So it was almost like I manifested it into reality. What I was hoping A would be, B ended up being. So I had my answer here and I was done. But okay, you don't really care about how I came to the solution. If you're watching this video, you're probably more interested in kind of reviewing these concepts and looking for hints and tricks in solving these things. So let me go back into this in a little bit more detail. So first, this notation right here just means we have this sequence of numbers. It could be really basic, like, I don't know, an equals n squared, in which case the first term in the sequence when n equals 1 would just be 1, the second would be 4, the third would be 9, and so on. It could also be something that's not defined so explicitly, like, I don't know, an could be the nth prime number. So the first term in the sequence is 2, and then the next is 3, and then 5, and 7, and 11, and so on. All this is an infinite ordered collection of real numbers. Two important properties for sequences are the idea of convergence and the idea of bounded. Informally, a sequence is convergent if it gets and kind of stays arbitrarily close to some number. Maybe I'll say some number C, in which case C is the number that the sequence converges to. A sequence is bounded, kind of as the name suggests, if there are two numbers, your sort of upper bound and lower bound, that the sequence stays between. So for the two examples I've given so far, this sequence is divergent because it doesn't get really close to some number, it gets infinitely large. And it's unbounded because, well, it does have a lower bound. 1 would serve as a lower bound. It doesn't have an upper bound. Right? Pick whatever large number you want for the upper bound, and I could find an n so that n squared is greater than your number. Actually, same idea over here. This thing's not convergent, and this thing's not bounded. Maybe we can consider one more sequence real quick. How about 1 over n? Sure. So the first few terms in that sequence would be 1, 1/2, 1/3, 1/4, and so on. And maybe you can see that this sequence would be convergent. It converges to the number 0, and bounded. It's bounded above by 1, and it's bounded below by 0. Anyways, when you're thinking about divergent sequences, all a divergent sequence is one that's not convergent. So a sequence that doesn't get arbitrarily close to some number C. They kind of come in two flavors. They're good kind of counterexamples to keep in mind. One we've already seen, a sub n equals n squared, or just n, or whatever. This type that kind of goes off to infinity. But there's another type, an interesting type of divergent sequence that's bounded. And that's the type that just kind of oscillates between some set of numbers. So -1 to the n power is a common example. Another common example would be what? Sine of pi n over 2, right? When n equals 1, the sine of pi over 2 is 1. When n equals 2, the sine of pi is 0. Sine of 3 pi over 2 is -1, 0, 1, 0, -1, and so on. This one kind of bounces back and forth between these three numbers. I think with that in mind, we can go back and visit A and B here. Every unbounded sequence is divergent. Yeah, absolutely that's true. Because if it's unbounded, then there's not either an upper bound or a lower bound. Say there's not an upper bound. What that means is the terms in the sequence get arbitrarily large. So they can't possibly converge to some real number. I guess that's worth putting in here. So unbounded certainly implies divergent. But that kind of brings up a larger point. On this test, there'll probably be several of these questions where you're evaluating the validity of a bunch of different statements. And often those statements come in the if-then form. Something that I find really helpful when you're trying to evaluate the validity of if-then statements and you're struggling is to consider the contrapositive. So a quick refresher then, if you have a statement like P implies Q, the contrapositive is not Q implies not P. And these are always equivalent. If a test question gives you P implies Q, and you can't tell whether that's true or false, you might want to rewrite it as not Q implies not P, and see if that's easier for you to evaluate the validity of. Because if this one's true, this one has to be true. If this one's false, this has to be false. So like in this example, every unbounded sequence is divergent. You could rewrite that as unbounded implies divergent. In other words, unbounded is P and divergent is Q. If I was unclear about whether that was true or false, I could say not divergent, aka convergent, implies not unbounded, aka bounded. Maybe it's easier for you to see that this is a true statement than it is for you to see that this is a true statement. They're both true statements, therefore they're not the answer to this question. B, however, says that every bounded sequence is convergent, and that's the one that I already talked about being false. In fact, I've already given an example of a bounded sequence that's not convergent. That's this one right here, right? It's clearly bounded. It's bounded above by 1 and it's bounded below by -1. But it's also not convergent. Why is it not convergent? Because we can play this little game where you tell me what it converges to. You pick some real number C that it's supposed to get really close to. I don't know what you'd pick. Maybe you'd pick 0. And I'd be like, okay, now it's my turn. I get to choose whatever small number I want, and you have to show me some point in the sequence so that all numbers after that point in the sequence are within that small amount of 0. I'm going to choose 1/2. There's nowhere you can go in the sequence where all of the terms of the sequence are within 1/2 of 0 because this thing oscillates between 1, 0, and -1. There's nothing special about 1/2. I could have picked 1/10 or 1/1,000,000th. The point is, it's not convergent. Again, if you struggled evaluating this, what's it say? Bounded implies convergent. You could rewrite it as not convergent, in other words, divergent, implies unbounded. And maybe it's easier for you to see that that is clearly false. Right? There's two flavors of divergent sequences, the unbounded type and the bounded type. This is false. This is equivalent to this. So this is false. Because it's false, B is the answer. We know the answer, so we're done with the problem, but it's worth going through C, D, and E. We know they're all going to be true, but we should still argue about why they're true in case that knowledge serves you in a different problem. So C says, if the limit as n approaches infinity of a(n) equals a, in other words, if my sequence converges to the number a, and there's some function mapping the reals to the reals that's continuous at a, then the limit as n approaches infinity of this new sequence is equal to that value f of a. This is a true statement, and really it just comes down to this word continuous here. What it means for a function to be continuous, again informally, is that the outputs of the function get arbitrarily close to each other anytime the inputs of the function get arbitrarily close to each other. So like a classic example of a continuous function is f of x equals x squared. If I pick two different x values that are really, really close, I don't know, 2 and 2 point, a bunch of zeros and then a 1, then the corresponding y values are going to be really, really close. 4 and, can't do this math in my head, all right, because these two are close, these two are close. Again, I'd encourage you to look up a more concrete definition and make sure you understand it with all the math, but this is the idea of what's going on. So in order for this sequence to converge to A, the terms of the sequence are getting really, really close to this A when n gets really large. Well, because my function's continuous, the fact that the terms of this sequence get really, really close to A means that the terms of this sequence get really, really close to wherever my function sends A. Right? In your head, maybe think this sequence is, I don't know, 3.1, 3.01, 3.001, 3.0001, right? It's clearly getting really, really close to 3. And the continuous function that we'll consider, I don't know, f of x equals, let's say x cubed, just to mix it up. Well, if I cubed all these numbers, this number would be pretty close to 27. I think it ends up being like roughly 29 or so. And then 3.01 cubed ends up being like 27.2 or something. 3.001, now we're in like the 27.01, I don't know. I don't know exactly what these numbers are, but the point is, the fact that these are getting really, really close to 3 means that these are going to get really close to 3 cubed. In other words, 27. What about statement D? Statement D says, if the limit as n approaches infinity of a(n) equals a, in other words, the sequence converges to a, then for every epsilon greater than 0, there's a positive integer k, such that the absolute value of am minus an is less than epsilon whenever m and n are greater than or equal to k. This is almost exactly our definition of convergence here. So what this is saying, to kind of translate it, is we have this sequence and the sequence converges to a. Then for every epsilon greater than 0, you get to choose whatever super small number you want. I can find some point in the sequence so that anytime we consider two terms later in the sequence, the distance between those two terms is less than this tiny little number you pick. The way you can kind of think about how this works is, say you pick epsilon equals, what's your favorite small number? 0.01? Sure. Well, what I will do is I'll consider half of that number. Maybe we'll call it epsilon prime equals 0.005, right? Because this sequence converges to A, I know that for any epsilon, namely epsilon prime, I can find some point in the sequence K so that any number in the sequence, maybe we'll call it A sum M, is within this tiny little epsilon of A, what this thing converges to. Another way to say that is A sub m minus A absolute value is less than this 0.005. This is true for any m after the k that I pick. It's also true for any n after the k that I pick. But if this number is within 0.005 of A, and this number is within 0.005 of A, then these two numbers must be within 0.01 of each other. Right, because worst case scenario, this thing is 0.005 bigger than A and this thing is 0.005 less than A, then the distance between these two things are 0.01. Finally, E, what E says is, we have the same statement here. The limit as n approaches infinity of A sub n equals A. In other words, the sequence converges to A. If and only if the limit of this new sequence, the absolute value of A sub n minus A, is equal to 0. The if and only if kind of makes you want to go in both directions. So maybe I call this side P and call this side Q. We can kind of talk through a P implies Q argument. If this sequence converges to A, then these terms are getting arbitrarily close to A. So if I took these terms and subtracted A, I'd get arbitrarily close to 0. P implies Q. What about Q implies P? If the limit as n approaches infinity of the absolute value of an minus A equals 0, in other words, the distance between these terms and A approaches 0, then the sequence itself converges to A. Yeah, absolutely. The way the distances get close to 0 is if the numbers approach A. Q implies P. These are really just two equivalent definitions of convergence. I intentionally made this as informal as possible, but I'd encourage you, if you need a little bit more review on these, to look up the formal definitions of convergence and boundedness and continuity and really make sure that all my kind of informal arguments track. It's not something you'd want to do on a test. On a test, you'd want to understand these concepts well enough so that you don't need to do that. But I think it could strengthen your understanding if this stuff's a little bit shaky for you.